Okay. So I hope that we can see this. I try to make it small so we can see this chart down here at the same time. So hopefully we can, I can make it a little bigger. So to begin, we're doing chemical periodicity, which is the trends. It's just more trends that we can find on the periodic table. So sometimes you'll hear this being called the periodic trends. It's based on these arrows down here, and we can find different elements on the periodic table, and based on where they're at, I know what their atomic radius will be, or about, and their ionization energy and their electronegativity. So those are our three trends. So as we go through this, the two things we're going to focus on is fluorine and francium. So those are two elements we're going to focus on. Fluorine is really little but strong, and francium is really big but weak. So when I say focus on fluorine, I'm even going to kind of box them on my periodic table, and you might want to box them on your periodic table. This is fluorine right here. That's fluorine. And then francium is the one at the bottom. Okay. So francium is really big and really weak for all these trends we're going to talk about. It doesn't have a lot of energy, and its electronegativity number is really low. But it is a very big atom. Whereas fluorine is really small, but it actually is really strong. It has a really high ionization energy and a really high electronegativity number. Now we're going to talk a little bit about why, but not a whole lot. It's kind of above our heads at this level in chemistry, but I'll talk about a little bit of why as we go through it. So atomic radius is the first one. Atomic radius, if you know what radius is from geometry, it's this right here. That's radius into the center. So if we're thinking the center is the nucleus, and then out to the outermost shell of the electron cloud, measuring that is the atomic radius. So basically, when we're talking atomic radius, we're talking about, I'm going to put an S there, should be a Z. We are talking about size. So the size of the atom, okay? Now, as you go across the table, so going, I'm going to do which way it gets bigger. So if I go this way across the table, the atoms get bigger. And if I go this way across the table, the atoms get bigger. So I'm going to draw that in down here on our chart. So down here, the ones that are going to the left and going down are these two. So this is atomic radius getting bigger. And this down here is atomic radius, and they're getting bigger, going that direction. Now, why they're getting bigger, this one's pretty obvious because we know our energy levels. This is energy level 1, this is energy level 7. Well, energy level 7 means it's 7 energy levels away from the nucleus. So 7 as in like distance away from the nucleus. So if you're way down here like francium is, well, you have 7 energy levels. You're obviously going to be a pretty big atom. Whereas if I go up here to fluorine, well, it only has 2 energy levels. So it's going to be smaller, obviously. So this one makes a little more sense.
Come on, I'll give you a chance. What are you going to do?
I'll do this weekend.
Okay.
Sure, I'm gonna do the switch. I don't get the correct.
Y'all need to come in here? So I was trying to record.
Oh, there's a, oh, we'll shut this door.
Yeah, I was like, sorry, I was like, recording the video for tomorrow.
I like your boots.
Thank you. Yeah.
Yeah.
Sorry, guys. This is after school, and some maintenance people tried to come in. So anyways, if I'm looking at chlorine versus sulfur, so chlorine is, where is chlorine at? Chlorine is right here in green, and then sulfur is right next to it over here. So this is chlorine and sulfur, come in different colors. There we go. All right, now when I'm looking at my arrows, well, going this direction, they get bigger. So if it says which one is bigger, well, it's going to be the red one. The red one is going that direction, so the red one is sulfur. So sulfur is going to be bigger. Then if I go the other way, so now I have chlorine versus bromine. So chlorine is still in the same spot as the green one. Bromine is down here, it's below it. So now again, we look at our arrows, and remember, down over here, if I'm going down the table, it's getting bigger. So chlorine was green, bromine was red, bromine is further down, so bromine is bigger. Okay, so it's really it, you just follow the arrows. Now, for ionization energy and electronegativity, it's the opposite of going that way, as you can already see from the arrows on our little chart down here. Ionization energy is the amount of energy required to remove an electron, okay? So it's how much energy it would take to steal something's electrons. Some atoms have a really high energy, it's like almost impossible to take electrons from them, and other atoms have a really low energy because they actually want their electrons to be taken. So as an example, let's say sodium. Sodium has 1 valence electron. Remember from our previous unit, past couple days, it wants 8, but it can either lose 1 and have a full undershell of 8, or it could gain 7. Which one's easier? Losing 1, the energy to lose 1, or the energy to gain 7? Well, 1 is a lower number. It's going to take me less energy to do that. So sodium ends up losing that 1 outside electron. It loses it, gives it to someone else, and becomes positively charged. So all of the atoms that are positive on the periodic table, which is really all the metals, all of them actually want to lose electrons. They're wanting to lose 1 or lose 2 because they're all trying to get that stable octet by losing their atom of electrons and having the full shell underneath. So their ionization energy is low because they actually want to lose electrons, okay? Whereas when I get to like fluorine, which actually is the highest highest ionization energy and highest electronegativity on the table, fluorine, remember, has 1, 2, 3, 4, 5, 6, 7. It has 7 valence electrons. So if it has 7 valence electrons, all it needs is 1 more, just 1 more electron. So there is no way that it's going to want to give an electron away because it's trying to gain 1. It's trying so hard to gain 1 to have a full octet. So its ionization energy is really, really high because it doesn't want to lose any, it really wants to gain. So things that are negative that want to gain, so it wants to gain 1 and become negative by 1, things that want to gain electrons have a really high ionization energy, okay? So to kind of put that on the table now, if I'm going this direction, they have more ionization energy heading towards the nonmetals. And again, going up, they have more ionization energy getting closer to the nonmetals at the top. Because again, we're focusing on fluorine. So fluorine, remember, is right here in blue, still the blue circle there, and it is over this way and up this way. We're focusing on fluorine. Fluorine is always the strongest, the tiniest, but the strongest, has the most ionization energy and the most electronegativity. So I'm going to add that to our table now. Ionization energy. And over here too. Ionization. Not letting me write so small. Energy. I'm not trying to, just looks so terrible. Ionization energy. Okay, sorry, it's really hard to write on those arrows sideways on the smartboard. So if I'm looking again at the periodic table, let's erase our previous dots. So we have new ones to work with, but I'll put fluorine back. So I'm looking for the largest ionization energy. So remember, it's going this way and going up. So I'm looking at oxygen and nitrogen. So oxygen is right here. That's oxygen in green. And nitrogen is right here in red. So if I'm looking at the arrows, it says it gets up as I go this way. So oxygen, in this case, has more ionization energy. Whereas oxygen versus sulfur, so oxygen's still in green, but we're going to put sulfur down below it. Sulfur's there. So it goes up. See here, ionization goes up as I get closer to fluorine. So now the red one being sulfur and the green one being oxygen, oxygen is still higher. And oxygen is really close to fluorine. The closer you are to fluorine, the higher the energy you have, because fluorine is the highest. So if it's getting closer to fluorine, then it probably has the highest too. Okay, so that's why it says focus on fluorine at the top, because the closer you get to fluorine, the higher ionization energy something has. The further away from fluorine you get, the less ionization energy something has. Okay, let's erase those again. Just scrolling down, so electronegativity is our last one. It's almost the same as ionization energy. What it says is electronegativity is the attraction of an atom to electrons. So how much do they attract other electrons? Like what is basically like their magnetic pull on other atoms or on other electrons. So if I'm going this way, it's going to be more. They're going to have a higher pull. And if I'm going this way, it's going to be more. Going to have a higher pull. So it's the same direction as electronegativity was. I mean, ionization energy was. They go the same way. So we're going to add that to our table now. So electronegativity. And the same thing over here. I guess I could go it this way. Doesn't really matter. Electronegativity. Okay, so electronegativity going up. So now I'm looking at our arrows, and for these elements, we got magnesium and sodium. So magnesium is right here in the green circle that I'm circling, and sodium is over here next to it. Okay, so if going this direction, we get higher electronegativity, then the one with the larger electronegativity would be the green one, which was magnesium. So magnesium has one. Now we're going to do potassium, sodium. So sodium is in red, and potassium is below. Ooh, same color. There we go. Okay, so potassium is in green, and sodium is in red. Now, as I go this way up the table, we get higher electronegativity, closer to fluorine. Remember, I focus on fluorine. So the one higher up is closer to fluorine, so that's going to be sodium. Sodium is above potassium. There you go. Okay, so we filled up the table. That's really all you do is you follow the arrows. I would recommend adding all of these to your periodic table. So putting ionization energy, electronegativity, adding all those things to your table so you don't have to pull up notes every time. So the one that we've been routinely adding stuff to your periodic table, I'd add those arrows and trends and their names so that you have it.